First, let's talk about the parent constraint. Before we make a parent constraint, let's go ahead and create a regular parent relationship first. This is because we'll need to use this parent relationship to compare with the parent constraint later. We've already gone over parent relationship in an earlier section, so let's just quickly review it together. We select our child object, and then select parent object. Press P on the keyboard. We can see in the outliner these two have formed a hierarchy. Okay, next, let's create the parent constraint. Here's something we need to pay attention to. Unlike the parent relationship, for parent constraints, and really for all constraints, the selection order is to first select the driver object, and then select the driven object, then create the constraint. It's the exact opposite of the parent relationship. So here, we'll first select our driver object, which is this big box, and then shift select our driven object. Then in the menu bar, find constraint and find parent. Go to the option box next to it and click that. For now, let's just reset to the default settings. We'll go over what these different settings do one by one later on. Go to Edit and find Reset Settings, and then just select Apply. Parent constraint, just from the name we can probably guess. It has a lot of similarities with the parent relationship. I mean, their names are almost the same. Well, to put it simply, the parent constraint is basically just simulating the parent relationship behavior. So as we can see, if I select the parent object, or in this case, the driver object, when I translate it or rotate it, the result they produce is pretty much identical. But what we need to look at here are the differences between them. The first difference, I'm sure, is pretty easy for us to spot. When we scale, we can see with our parent relationship, the child object will scale up or down right along with the parent. But with the parent constraint, the driven object doesn't have this behavior. Also, when we select the parent object in our parent relationship, our child object actually gets selected too. This is just a feature of Maya. When we select an object, all the child objects under it in the hierarchy will also show up as selected in the viewport. But our parent constraint, it doesn't have this. Our driven object looks like it's still a separate independent thing. Next, let's look at the outliner. From the outliner, we can also see what we were just talking about. With the parent relationship, these two are in a hierarchy. Our child object is under our parent object, forming that tree structure. But our parent constraint is totally different. They are at the same level in the outliner. And our driven object, if we click open this plus sign, we can see there's an extra node underneath it. This node has a little chain icon, and its name is parent constraint. So let's select this node and press Ctrl+A to go to the attribute editor. We probably still remember in the attribute editor, the word to the left of the name shows its node type. So here we can see its node type is parent constraint. So what's really going on with their relationship? Well, the two objects actually exist independently. The reason they have this constraint effect is because we created this parent constraint node, and it connected the driver and driven objects together. Okay, so let's keep observing. Let's take a look at our parent relationship's child object. We can see its channel box is very clean. There's nothing on it. For example, if we create a brand new transform node, we can see that it also has nothing on it, just some values. But when we look at our parent constraints driven object, we see it's different. Its translate and rotate attributes have turned this light blue color. What does that mean? Now, since we haven't gone over attributes in detail yet, for now we just need to know that when a color appears on our attribute values, usually it's something like blue, yellow, red, and so on. It generally means that these attributes are being controlled by another node. Another node will do some calculations and then feed its value into this attribute. And these attributes then becomes non-editable. So here we can see its translate and rotate are affected. The light blue just means these attributes are constrained. And as we know, we created a parent constraint node. So these attributes are all connected to that parent constraint node. Next, we can see its scale is not connected to any node. So this explains one of the differences we just found. We should still remember, we saw that when our parent object is scaled, child object scales right along with it, no matter which axis. But parent constraint doesn't have this feature. When we scale it, our driven object will only translate along with it, but it won't scale at all. So, How is this translation happening? This is actually, as we just said, the parent constraint is simulating the behavior of a parent relationship. Here, when we scale them together, we see the child in the parent-child setup not only scales, its word position is also changing. So here, since the parent constraint is simulating this behavior, its translation will also change. The translation is controlled by parent constraint node. That's why its value here will change. But this constraint node doesn't control scale, so the scale here won't, like the parent relationship, change in size. Let's keep going. So we also observed earlier that in our parent relationship, the child object's own channel box is very clean. It's not controlled by any node. At previous sections, we also talked about a feature of parent relationship. Our child object within the parent space has its own freedom of movement. When we move or rotate our parent object, our child object can also be moved, rotated, or scaled under the parent's hierarchy. But let's look at parent constraint. Here, we already know that its translate and rotate are controlled by the parent constraint node. This means it can't really be moved independently anymore. We can try it out. When I move or rotate the driver object, and then try to move or rotate the driven object, it looks like we can still do it. But watch, as soon as I move the driver object just a little bit, we'll see it automatically snaps right back. Why is that? It's just like we said, because its translate and rotate are being controlled by the parent constraint node. And our parent constraint node is always calculating a result based on the driver object. So even though we've temporarily moved it to another position, as soon as our driver object's translate or rotate is updated in any way, that calculation has to be redone. And when it does this calculation, it doesn't take into account any of our recent edits. So it will override those values and jump right back to its own calculated result. So this is another really big difference between parent constraint and the parent relationship. With the parent relationship, the child object can have its own translate, rotate, and scale under the parent. But the parent constraint doesn't have this feature. The driven object will always follow the driver object closely. And this feature is not just for parent constraints. All constraints have this kind of behavior. That's something we need to keep in mind. Next, let's look at this scenario. So here, I've again used my big box to create a parent constraint on the small box. What's different is, because we know with a parent constraint, in the outliner they're at the same level. So I put each of them under another object as a child object. Small box is placed inside this blue circle as its child, and the big box is placed inside this yellow circle as its child. So the question now is, the big box has a parent constraint on the small box, but at the same time, we see blue circle is the parent of the purple small box. So who does the purple small box listen to? Who does it follow? If we move our big box, does our small box follow the parent constraint and move? And if we move our blue circle, does our small box also have to follow the blue circle and move? Well, we can just test it out and see. Here, we move our big box, which is the driver object. And we can see our driven object still follows our driver object. So the parent constraint is still working in this situation. But when we move the circle, we find that the small box, our child object, no longer follows the parent object. Instead, it stays right where it is, and only when we move our driver object, it moves along with the parent constraint. So this brings up a really important feature of constraints. And this isn't just for parent constraints, it applies to all constraints. So we need to remember, constraints will override parent relationship. They have priority over parent relationship. What this means is, our driven object in workspace will always follow our driver object, regardless of how many parent levels it has above it. That relationship will be override by our constraint, and it will follow our constraint instead. So that's what happens on the driven object side. Now we also see our driver object also has a parent object too. The question now is, when we move this parent object, it's not directly moving the driver object itself, because its values, as we know, as a child of another object, its translate, rotate, and scale values won't change. So when we move the driver object's parent, will the parent constraint still work? Let's try it. When we move our driver object, the parent constraint works. And when we move our driver object's parent, we can see it is still effective. And here, if I group it again and move this group, so that's another parent above the driver object's parent. If we move that, it also still works. This is another feature of our constraints, not just parent constraint, but all constraints. A constraint is a constraint in absolute world space, not a relative position. Look here, no matter how many groups I have above it, the final result is that my driver object's absolute world position has changed. As long as this absolute world position changes, it will affect my driven object. And my driven object, no matter how many parent objects above it are controlling it, its current absolute world position will always be following the driver object's position closely. Another point I'd like to point out is this. When we talk about parent relationship in the previous section, we said the child's translate, rotate, and scale are relative to the parent. So its values here are its relative position to the parent. So what we need to pay attention to here is, when we move our parent object, the child object, because of the parent constraint, will stay in its original place. But at this point, we need to watch its values. Its values are going to change. For example, I'll move it up by 5 units. Then our child object, in order to stay in its original place and follow our parent constraint, its translate y has to move relatively down by -5 units to keep it in place. If this is 10, then this will also become -10. So this value is constantly changing because it's a relative position to the parent object. It's like this. For example, I'll duplicate 1 over here. Look, when I move it up by 5 units, our child object, because it follows the parent, it will also automatically move up 5 units in absolute world space. Here it still keeps its default value, no value change. But because we have a parent constraint, we need to ensure it stays in place and follows the driver object. So here we need to move it down by 5 units to keep it in place. We should all pay attention to this value change. It's not static. When our parent object moves, even though the child object stays in place because of our constraint relationship, its values are constantly changing. So when necessary, we can also use this method to extract some relative, translate, rotate, or even scale values to get us ready for more complex operations later on.